Hey, welcome back. So, what we have seen so far is the sign type data and verification part of things. Like we were doing verify type data inside the Hub-Monorepo. In crypto, EIP 712. Now, let's get to ED25519. This is even simpler. You just import the ED25519, get the public key, safe sign, and then safe verify. Get public key, safe get public key from private key, sign message hash, you give the hash of the digest to be signed and the private key, it will return you the signed message, and verify, you pass in the signature hash public key, it will return you the verification. So all the three functions are here only: get public key, sign message hash, and verify message hash signature. Unlike EIP 712 module where it is primarily about verification, signature is something you have to generate from the outside and send in. So we have done EIP 25519 712. Let's see what the test is all about. Private key, you have an account, you have a signer, and then you write a bunch of tests. Next would just be about exporting this all out. Fine. So crypto piece is done. Now let's finally get into signers and quickly wrap this up. ED25519 signer, get in the signature scheme, get in the signer from dot signer. What is dot signer? Signature scheme from protobufs, and an interface signer where you need to provide in scheme, and it defines two methods: get signer key and sign message hash. Two 56-bit signature is generated for a message hash and returns the bytes. Okay. If we take come back slightly higher, zoom out and go back in, what exactly is going on? This is something we have seen. Herein was your verify ETH address claim and so on, wherein you're using VMs verify signed typed data. Now once the cryptography part is set in the folder, then we move on to finally the signers folder. Let's see what the logic here is. First thing that we are seeing is dot signer which is just an interface of three things. Like an abstract class, signature scheme, which can either be this ED25519 or EIP712. Second is the get signer key. Third is the sign message hash. This is a 256 bit signature. Get signer key is the key in bytes used to identify the signer. Okay. Straightforward. So now this signer would be important to these two, like either it can be a 25519 signer or a EIP712 signer. Let's see how it builds out. Protobuf error signer, you put in the 25519 signer and that interface is implemented by this abstract class. So it needs to put in the three pieces of information as concrete values. One is signature scheme as defined in the protobufs. So this is a ED25519, you put that as the signature scheme and get the 256-bit public key in bytes as well as this sign message hash. This is the get signer key. Will be a uint array, uint8 array, and sign message hash again, the same thing. You give it a hash, it will return you the signature. Similarly, we have a EIP712 signer. Protobuf errors, verification address claim, as we had seen earlier, like this piece. Username proof claim, signer, key gateway, add message, key registry remove message, ID gateway register message. These are a bunch of on-chain interactions. ID registry change recovery address message and so on. So these are related to on-chain interactions. Signed key request validator, signed key request message. So we are now extending this class to implement an EIP712 signer. The EIP712 signer implements a signer. The scheme is EIP712. This is clear. Get the 160-bit address in bytes. Get signer key, sign message hash, and then a bunch of new functions that are present here to do on-chain verification. Sign verification address claim. You pass in the claim, you pass in the chain ID, it will return you the signature. Sign username proof claim, sign register. I think this is for ID gateway register message to register a new FID, to add key, new key against your FID, to remove a key, to transfer a key and transfer and change your recovery address. So all the functions that are defined in the on-chain contracts, this is the module that creates EIP712 signatures for all those functions. So that user can sign this and then this signature is passed on onto the contract, therein it's verified and the necessary action is taken. If we see here, signer, EIP712 signer. The three contracts that are present on chain will be your ID. Let me make this, the contract says green. Key. Third one would be storage. Like you register, like generate an FID basically. Add a key against this register means like you have now an FID. Let's say 2242. Add a key like 0x123, add it to 2242. Then you have the remove part of this. Let's say someone wants to remove 987 from 2242 and so on, like all the other functions that are defined in this contract. So those are your sign add, sign remove, sign transfer. Let's say you want to transfer it. You want to transfer your FID. Like transferring your FID would essentially mean like this address or Ethereum public key is assigned to this FID. You want to shift this to some other FID. Let's the 786. This is the transfer. Similarly, there is a bunch of transfer and recovery related things if you want to remove all that. So all these different functionalities are available in one of these three contracts. They need an off-chain signature which is then verified on-chain. So you create this EIP712 signer, do the signature, pass it to the contract, it does verification and takes the relevant action. So now Ether's EIP712 signer. I think it uses Ether's library. Yes, type signer from Ether's. Verification and same Farcaster domain. All this EIP712 related like structure type data. All the structure provided. Contracts. ID registry. Signed key request validator. Ether's EIP712 signer. You pass in the signer through the constructor to basically instantiate this class. Minimal ether sign. Okay, get signer key, sign message hash, await result async from promise. Ether signer dot sign type data. Okay, so this is implementing through Ether's library. Sign verification ether address claim. You pass in the claim, chain ID, and then it takes what the domain is from the chain ID, takes in the signature and then converts it to bytes. Sign verification address claim, username proof claim. So all those functions that we just saw, this is implementing every one of that function, like just taking a message, passing in a signer and creating the signature for the type data of different types. Key gateway add type. So add a key is your data, and the message it's creating a signature on top of it. Right. This is again straightforward. Just similar to Ether's EIP712 signer. Now Ether's V5. Okay, Ether's has V6 and V5. There are a bunch of changes to that. It is implementation of signers for a user using different libraries. Ether's, this would be Ether's V5 if I'm not wrong. Where are you? Ether's EIP712 signer, Ether's project abstract signer. Everything else remains the same, and again those functions are implemented. Class constructor get signer key, sign message hash, sign verification ether address claim. Right. Signed key request metadata. Oh, what is the most relevant for us in fact is the signed key. Sign key request. As an app, a Nenar makes this. Yes, these are the two things that's actually the most relevant for Nenar. So what Nenar cares about is a sign key request and a get signed key request metadata to create their managed signers. Right, so we need to dig a bit deeper into these two functions. AIP central signer using ethers. Let's get into it. The last two functions. Sign key request. So your message is a signed key request message. Where is this coming from? Signed key message request. ETH contract signed key request validator. Okay, we have skipped over this, but unsurprisingly, this is more important. Let's quickly check it out. ETH contracts signed key request validator. If I type data from VM, signed key request message. Okay, this is the message that is generated. FID of the user or app requesting the key. Bytes of public key. Unix timestamp when this message expires. So let's say my multilingual cast translator app is the one that is requesting from the user. This will be my FID. Then there is a key, bytes of public key. I don't know yet what this is. Unix timestamp when this message expires. Signed key request validator address. Okay, this is the contract that validates the request. Signed key request validator EIP 712 domain. Signed key request validator version chain ID verifying contract is this one. This is fine. Signed key request type. There is going to be an FID, a key, and a deadline. Signed key request validator EIP 712 types. There are two things in this. One is going to be the domain, this, and one is going to be the types. Again, this is very standard EIP 712 requirements that you need to pass in a domain and types. Verify key request message. Signed key request message. This one. Signature address. Valid is equal to result async from promise. Verified typed data. Address. Domain. Types. Primary type is signed key request. Fine. Pass in the message. Message contains this. And key I convert to hex. Message.key and the signature. So again, this is not creating a signature, it's again just verifying the key request. So let's go here and see how the signature is created. Sign key request, right? So message, this message is passed that hey, this is the request FID and this is the key against it, and this is the deadline. Based on that, it is signer.sign type data. Signed key request validator EIP central domain. Alright. Signed key request. Signed key request type. This entire piece is provided. Again, the same like domain and the types is what we are providing. Message, and then hex string to bytes. So convert it to bytes and return it. Question that I have here is this key. Signed key request message. This key is being signed against this FID. Get signed key request metadata. Let's quickly have a look at this as well. Signature bytes, sign key request. This is signature bytes to hex string. Okay, converted to hex. Signer address bytes. This dot get signer key. Signer address. This dot get signer key. Request FID, request signer, signature and deadline, and code struct. I'll slow down and do this again. Let's do this nice and easy. EIP 712 signer, which is being converted into this is an interface. FID key, oh no, this is what signature scheme, get signer key, get message hash. This is being implemented by ethers EIP 712 signer. Now this has all those bunch of functions. Sign. Those are pretty straightforward. Here what is confusing is like there are two things involved. One is the app that is requesting a particular sign key for a user, and the user itself. I'm unable to differentiate as to which is which and how are they interacting. So get signer key, all it does is ether signer dot get address and then converts the hex string to bytes. Fine. Sign key request. Let's do this. Sign key request. a request by an app to generate key on behalf of their user. Okay. And the signed key request requires a signed key request message. This requires a signed key request message. Now what does the signed key request message entail? A signed key request message is FID of the user or app requesting the key. This has three parts: FID, user or app requesting the key, second is the key. Third piece is the deadline. Message expiry. What is going on now is this message is generated. So let's say FID is 123, requesting FID. The key is 0x987 and deadline, let's say 365 days. Once this is put into sign key request, we are asking for a signature for the key request. So what we are asking is this packet to be signed. We are asking for sign key request. This is the key request. Alright. Now to sign this key request, what do we need? Ether signer.sign type data, right? This packet goes into ethers.sign typed data. So this is the message. And then we need to provide other things. This is the message. We need to provide in signed key request validator EIP 712 domain. Just validated EIP 712 domain. So this piece of information with the contract address and everything that is provided, and signed key request type. Signed key request type. So the other two arguments, like this whole packet, which is essentially telling Ether signer ki, hey, this is the domain and this is the structure of the data, request data that I have provided you. There is a request FID, there is a key and a deadline, which is absolutely fine. This is the request FID, the key and deadline. This is absolutely fine. So far so good. All it does is creates a signature and returns hex string to bytes. It converts this hex into bytes and returns it. Okay. So what is going on here is this signer has that particular method. This is the signer. It has sign key request method, and it is inside this method that we have request FID. I think this would be the address that we want. Like this is the key that which is signed. This is a key request. So this app FID, from its own FID, it is for the user generating a key. This key must definitely, I think, be the apps key for user. While this is app FID and then the deadline. The question is the signer what is this signer entity in itself? AP central signer, it's a bunch of methods. Like who is this generated for? Get signer key. It's an ether signer. This would definitely require some sort of public private key in itself. Where is that being generated? Constructor signer, this dot ether signer. Okay, so at the time of instantiation of this class only, I'll be providing it with a public private key pair. Right. So what would be happening from application level is, I think what would Nanar be doing? Yeah, even me as an app. This is Nanar would have its own private plus public key, and this private and public key would be generating from, let's say, the Farcaster mnemonic is generating this public private key pair that is being used to instantiate the signer. For Nanar. So the flow would look like, let's say I have an app, my multilingual app, let's say Glotsphere. What I should do ideally is have an FC account for this. So I will have a Farcaster mnemonic, which I will use to generate my public private key, which then I use to generate my signer, ethers or VM, whichever it is, ethers EIP 712 signer. And inside the signer I have a sign key request, wherein, so this then I think this is this then would it be app FID or would it be users FID? This is a bit confusing. Here they are saying it's request FID for the app. Because I am doing that on behalf of the user. Okay, so this is something that I'll have to check. For now, I'm assuming that it is app. So this is Glotsphere has a GFID. Sign key request, it would go as GFID, and it would generate a key for the user. Zero x 987. Here in this public key is something else. This is 0x Globsphere key, which is the one being used by the signer. And finally the deadline, so it can be whatever. Okay, so this I think can be one flow. So I have the signer, I have complete control over it. I just pass in that, hey, this key, assign it against this GFID. But then every time I cast, how is that being linked from users, like casting on behalf of user? This is something I need to still clarify. Alright, this is clear. A signed key request is fine. Signed key metadata. Get signed key request metadata. Signature bytes. This to signed key request dot message. Okay, you got the signature. Got the signature as hex. Signer address bytes. This dot get signer key. Signer address, right. So signer address will be 0x GS key. Metadata struct request FID. Message dot request FID. Request signer, this signature deadline. Encoded struct, encode AVI parameters, request FID, request signer, signature deadline. Signed key request metadata, and then metadata struct x string to bytes encoded struct. And this piece is still slightly unclear. Let's check it out further through VM. Verify key request. This is the address of the signer. Domain type, primary type, message. Signature. Noble ED25519 signer. Fine. VM local EIP 712 signer. This is it. Bytes, everything remains the same. Verification address claim, all that. History, VM local EIP 12 signer, local account. Constructor get signer key. VM local account dot address, same thing. Sign message hash. Verification address claim. Still sign transfer. Sign key request. Sign message. So what I need to understand is signed key request the request FID inside it. Signature, device signer address, you do it, encode struct, sign type data. Sign type data, alright. Now I think we have enough context on the signer, and there's nothing more to be learned here from the specific query that I have with respect to Nenar's managed signer. So just to break it into the next part where I'll go through Nenar's managed signer codebase, I'll stop the video here and connect immediately into part 4, I think. Yeah, I'll connect after this.